In the first week of August, one of the most active volcanoes on Earth blew its top hard enough to send rivers of molten rock and superheated gas racing down 6 separate ravines at once, forcing 1,700 people out of their homes in the middle of the night. Around that same stretch of the calendar, roughly 93 million miles away, the sun was throwing its own tantrums, hurling bursts of charged particles toward Earth, strong enough to trigger geomagnetic storms and light up the sky with aurora far outside their usual range. 2 genuinely dramatic events, happening in the same general window of time, on completely different scales, involving completely different physics. And the honest, responsible thing to say about them is this: as exciting as it would be to tie them together into one single sweeping story about the sun triggering the Earth's volcanoes, that connection simply isn't something real science currently supports. Picture the two scenes side by side for a second, because they really do make for a striking split screen. On one side, a mountain in the Guatemalan highlands, glowing orange in the dark, sending rivers of fire down its slopes fast enough that entire villages had to be emptied in the middle of the night. On the other side, 93 million miles away, a boiling ball of plasma flinging pieces of itself out into space, some of that material eventually slamming into Earth's magnetic field and painting the night sky green and pink in places that almost never see it. Both are genuinely spectacular. Both are genuinely real. And it's tempting, almost irresistible, to imagine some hidden thread tying the two together. The sun acting up, the Earth acting up right along with it, as if the whole planet were somehow plugged into the same outlet. That image is dramatic. It's also not how any of this actually works, and it's worth understanding exactly why. Let's start with what actually happened, because both halves of this story are genuinely worth understanding on their own terms, without needing an invented link between them to make them interesting. Volcán de Fuego in Guatemala is one of the most consistently active volcanoes anywhere on the planet, and it's been erupting continuously in one form or another since January of 2002. On most days, it produces small, regular explosions every 15 to 20 minutes, visible lava fountains, incandescent rock tumbling down its flanks, and rumbling detonations powerful enough to feel in your chest if you're standing anywhere close. That's its baseline behavior. But on August 3rd, it escalated well beyond that baseline, entering what volcanologists call a paroxysmal phase, a sudden dramatic intensification of activity, producing much larger explosions and far more dangerous flows than the volcano's typical day-to-day rhythm. Over the following 2 days, Fuego sent pyroclastic flows, fast-moving currents of superheated gas, ash, and rock that can travel down a volcano's slopes at highway speeds, as far as 7 kilometers down 6 separate ravines surrounding the mountain. Guatemala's Disaster Coordination Agency evacuated roughly 1,700 people from 18 surrounding communities, and the National Volcanology Institute, known as INCIVUME, declared an orange alert and closed a major national highway as ash and debris made the route impassable and dangerous. The eruption's most intense phase lasted around 50 hours before authorities declared it over on August 6th, though they specifically warned that the danger wasn't fully finished even after the explosive activity itself calmed down. Heavy rain in the days that followed could still trigger lahars, the volcanic mudflows formed when loose ash and debris on a volcano's slopes mix with rainwater and come rushing downhill with tremendous, often lethal force. This wasn't Fuego's first serious event, and it won't be its last. The volcano has erupted at least 79 times since the year 1524, according to historical records, making it one of the most extensively documented active volcanoes in the Western Hemisphere. Its most catastrophic eruption in recent memory came on June 3, 2018, when a sudden, massive pyroclastic flow overwhelmed nearby villages with almost no warning, killing at least 190 people. The deadliest eruption in Guatemala since 1902. That tragic history is part of why authorities responded to this August's paroxysm with such immediate, aggressive evacuation orders, rather than waiting to see how the situation developed. When a volcano has a documented track record of turning suddenly and catastrophically dangerous, the responsible move is to act early, not to wait for confirmation that the worst-case scenario is actually unfolding. It's worth understanding, too, how volcanologists actually see an eruption like Fuego's coming, because it's a genuinely different, more grounded kind of science than the vague, celestial explanations that sometimes get attached to these events after the fact. Volcanoes typically give off real, measurable warning signs before a major escalation. Increased seismic activity as magma forces its way through cracks in the surrounding rock, changes in the shape of the ground itself as underground pressure builds, and the volcano's flanks subtly swell or deform and shifts in the type and volume of gases escaping from the summit, all tracked continuously by networks of seismometers, tilt meters, and gas-sensing instruments positioned directly on and around the volcano. INCIVUME and similar monitoring agencies around the world rely on exactly this kind of direct, physical instrumentation, not celestial correlation, to issue the alert levels and evacuation orders that actually save lives when a volcano like Fuego suddenly intensifies. It's worth understanding, too, that Fuego wasn't the only volcano drawing attention around the world this particular month, because August 2026 has genuinely been an unusually active stretch for volcanic activity globally. In Indonesia, 3 separate volcanoes, Mount Ibu, Mount Lewatobi Laki-Laki, and Mount Semeru, all produced eruptions in rapid succession in mid-August, prompting safety exclusion zones and ash plume advisories across the region. In Italy, Mount Etna's own extended eruptive activity forced the closure of Catania's airport for an unusually long stretch, disrupting flights before activity finally eased enough for the aviation alert level to be downgraded. And in Hawaii, Kilauea has been cycling through a distinctive pattern of episodic fountaining at its summit throughout the year, pausing and then resuming lava fountains in Halema-Umayu crater. On a schedule, scientists at the Hawaiian Volcano Observatory have been tracking closely, with another episode specifically anticipated in the days immediately following Fuego's own paroxysm. None of this clustering on its own is actually as unusual as it might sound at first. The Smithsonian Institution's Global Volcanism Program, which tracks volcanic activity worldwide in cooperation with the U.S. Geological Survey, notes that there are typically 40 to 50 volcanoes in a state of continuing eruption at any given time across the planet, with roughly 20 of those actively erupting on any specific day. Earth, as a planet, essentially always has multiple volcanoes erupting somewhere at once. It's simply not something that makes the news unless a specific eruption threatens a populated area, disrupts air travel, or produces genuinely dramatic photogenic activity, the way Fuego's early August paroxysm clearly did. Now let's turn to the other half of this story, because the sun really has been unusually active this year too, and that part deserves its own honest explanation on its own scientific terms. The sun operates on an 11-year cycle of rising and falling activity, and the current cycle, known as solar cycle 25, has been producing a genuinely elevated stretch of solar flares and coronal mass ejections, massive eruptions of charged plasma and magnetic field launched outward from the sun's surface, sometimes directly toward Earth. When one of these ejections reaches our planet, it interacts with Earth's magnetic field, triggering what's called a geomagnetic storm. These storms are measured on a scale from G1, the mildest, up to G5, the most extreme, and they're capable of producing genuinely striking effects. Vivid auroras, visible far outside their usual polar range, disruptions to high-frequency radio communication, interference with satellite operations, and in the most extreme cases, real stress on power grid infrastructure. August 2026, specifically, has seen a mix of this kind of activity, though it's worth being precise about the actual scale involved, because solar storm can mean very different things depending on its intensity. Early in the month, a moderate G2 level geomagnetic storm was observed on August 2nd, following the arrival of a coronal mass ejection, and another G2 level storm arrived on August 8th from a separate, slower moving eruption. Later forecasts for the back half of the month pointed toward the potential for further storming around mid to late August, with activity in the moderate G1 to G2 range, genuinely capable of producing visible aurora at higher latitudes and some technical disruptions, but well short of the kind of extreme G4 or G5 level events that made international headlines earlier in the year, including a severe G4 storm in January that arrived far faster than initially forecast, driven by a particularly powerful, fast-moving coronal mass ejection. So both halves of this story are genuinely real, genuinely well documented, and genuinely worth understanding on their own terms. A major, dangerous volcanic paroxysm did strike Guatemala in early August, forcing large-scale evacuations and closing a national highway. The sun has genuinely been active this year, producing real geomagnetic storms capable of real, measurable effects on Earth's magnetic environment and upper atmosphere. What doesn't hold up when you actually look at the underlying science is the specific claim that one of these things is causing, or is likely to cause, more of the other. Here's why that connection doesn't work, explained plainly rather than simply asserted. Volcanic eruptions are driven by processes happening deep within the Earth. Molten rock, dissolved gases, and pressure building within a magma chamber miles beneath the surface until that pressure finally exceeds the strength of the rock holding it in place. Geomagnetic storms, by contrast, are an interaction between the sun's ejected plasma and Earth's magnetic field, occurring in the magnetosphere and upper atmosphere thousands of miles above the ground, with no direct physical pathway connecting that interaction to the molten rock system driving a volcano deep underground. There's a genuine, real scientific body of research studying what actually does trigger volcanic and seismic activity. Factors like the accumulation of internal pressure from rising magma, changes in local stress from nearby tectonic movement, and, in some specific, well-documented cases, subtle changes in stress caused by the gravitational pull of the moon and sun during certain tidal cycles. That last category, tidal triggering, is a real actively studied area of geophysics. But it involves the direct gravitational pull of astronomical bodies, a completely different physical mechanism from a burst of charged solar particles interacting with Earth's magnetic field far above the atmosphere. Geomagnetic storms simply don't reach down into a volcano's internal plumbing system in any way current science has been able to identify or measure. That's an important distinction to sit with, because it's easy for two genuinely dramatic events happening in the same general stretch of time to feel connected, even when the underlying physics offers no real mechanism linking them. This is a well-known pattern in how people naturally process information, sometimes called a correlation-causation error, noticing that two notable things happened around the same time and instinctively assuming one must have caused the other, even when a careful look at the actual mechanisms involved reveals no plausible physical link at all. Earth has volcanoes erupting somewhere on the planet essentially all the time, as the Smithsonian's own tracking data makes clear. The Sun, currently in an elevated phase of its 11-year activity cycle, has been producing geomagnetic storms with some regularity throughout this year. Given how frequently both of these things are already happening independently, it would actually be more surprising if a notable volcanic eruption and a notable solar storm never happened to occur within the same general week of each other, purely by ordinary statistical chance, than if they occasionally did. There's a useful contrast worth drawing out specifically from the Kilauea example, because it actually illustrates just how well understood some volcanic behavior can become through pure, ground-based monitoring without needing to reach for any outside explanation at all. Kilauea's episodic fountaining pattern this year has been tracked closely enough that scientists at the Hawaiian Volcano Observatory have been able to forecast the likely onset window of individual fountaining episodes days in advance, based specifically on the rate of ground inflation measured by tilt meters at the summit. Instruments sensitive enough to detect the ground itself gradually, swelling as magma accumulates beneath it. That's the kind of genuine predictive power real volcanology can achieve when it's grounded in direct physical measurement of the volcano itself, and it stands in sharp contrast to the vague, unfalsifiable nature of a claim like solar storms trigger eruptions, which offers no specific mechanism, no measurable precursor, and no way to actually test whether it's true or false in any given case. None of this makes either individual story less worth paying attention to. Fuego's early August paroxysm was a genuinely dangerous, disruptive event for the communities living in its shadow, and Guatemala's continued vigilance around the risk of lahars and the eruption's aftermath is a legitimate, ongoing safety concern, not something that ended the moment the explosive activity itself calmed down. The elevated solar activity driving this year's geomagnetic storms is a genuinely interesting, actively studied phase of the sun's natural cycle, with real, measurable effects on satellite operations, radio communications, and the visibility of aurora at latitudes that don't normally get to see them. Both of these are legitimate, fact-based stories, each grounded in real, well-documented science specific to its own field. What responsible science communication actually requires, though, is resisting the temptation to weld two unrelated, genuinely interesting stories together into a single, more dramatic-sounding narrative that the underlying evidence doesn't actually support. Claiming that solar storms are setting off volcanic eruptions without a documented physical mechanism connecting the two isn't a bold new discovery. It's the same basic pattern behind a lot of pseudoscientific claims that have circulated for decades, like the persistent, thoroughly debunked idea that the full moon causes a measurable increase in earthquakes. Real geophysicists have specifically studied that exact claim repeatedly, using large data sets of both lunar cycles and seismic activity, and found no meaningful statistical relationship once you account for how many earthquakes happen on an ordinary day regardless of the moon's phase. The honest, responsible version of a story like this one isn't the version that manufactures a dramatic, unproven connection between two real events. It's the version that takes each event seriously on its own genuine merits, explains the actual science honestly, and trusts that the real story, a major volcano threatening real communities, an unusually active sun producing real geomagnetic effects, is already interesting enough without needing an invented, unsupported link holding it together. There's a broader reason this distinction is worth caring about, beyond just getting one particular claim right. Misinformation that links unrelated natural phenomena together doesn't just muddy the water on a single topic. It tends to erode people's ability to correctly identify the warning signs that actually do matter. If someone comes to believe that distant, unrelated solar activity is a meaningful predictor of volcanic danger, that's attention and trust diverted away from the actual evidence-based warning systems, seismic monitoring, ground deformation tracking, gas emission analysis, that real volcanologists spend their careers building and refining specifically because those are the signals that genuinely do predict when a volcano like Fuego is about to escalate. Getting the mechanism right isn't just a matter of scientific pedantry. It's part of what keeps people's attention pointed at the warnings that actually work, rather than the ones that merely sound compelling. So if you're tracking either of these stories going forward, here's what's actually worth watching, grounded in what the real science and the real monitoring agencies are actually saying. For Fuego specifically, Guatemala's INCIVUMEC continues monitoring the volcano's activity closely, and the elevated risk of lahars following heavy rainfall remains a genuine ongoing hazard for communities near the volcano's ravines, independent of whether the explosive eruptive phase itself has calmed down. For solar activity, NOAA's Space Weather Prediction Center issues regular, publicly available forecasts tracking the KP index and geomagnetic storm probability, genuinely useful information for anyone hoping to catch an aurora display or simply curious about the sun's current behavior. Both of those are real, ongoing, worth-following stories in their own right. No invented, scientifically unsupported connection required to make either one matter.